Okay, yesterday I posted these or I guess it was the day before yesterday, I posted these to ResearchGate, and I said I didn't have any time to comment, but I post these diagrams here so that I can access them yesterday when I'd have more time to describe them. George Dishman added a comment. We're out again today, leaving soon, but although the diagrams look about right, the bottom 0, 0 point should be included. And I said, I agree. I've thought about that, but I was putting it off. Maybe I can address it sooner if the solution isn't too complex. Um, anyway, I was describing why all of the points on the light cone are going to be mapped to 0, 0. Basically, you can determine that by using L'Hopital's rule. And when I used L'Hopital's rule, I tried it. A two-dimensional analog of L'Hopital's rule is just taking that y over x and deciding I'm going to come along the path toward the point 1, 1 along an isocline of y, that is letting x equals, yeah, that was, okay, yeah, this is the isocline of y. X approaches 1 and y equals 1. And then we'd replace the y with 1 over x, divide, and we got to change it to divide to use L'Hopital's rule. 1 squared minus x squared to the power of negative 1/2. And then you take the derivative of the top divided by the derivative of the bottom. And when you do that, it gives you 1 minus x squared over x squared. And that point gets mapped 1 minus 1 squared is 0 over 1 squared, and that becomes 0, so it's mapped to the origin. So what I've done in Mathematica with some complaint, apparently Mathematica has no functionality where you can just put if phi is indeterminate, let phi equal 0. Instead, you have to ask whether head of phi is a symbol. Why? I mean, there's probably some other symbols that could be problematic, but for this purpose, this seems to be what finally fixed the problem. If head of phi equals symbol, then phi equals 0. I would rather be asking if it were indeterminate, but there does not seem to be any way of asking Mathematica if the variable is indeterminate. But it does allow you to ask if the head of the variable is a symbol. So I've only tested that with one thing. I made a table of cone points, and those cone points form a table going from 0 to 0.5, step 0.01 of negative I, 1 minus I, and then another table I, 1 minus I, where I goes from 0.01 to 0.5 to 0.01. I actually want to modify the cone point so that it goes left to right. I'll have it go from 0.5 to 0, step negative 0.1, 0.01, and then I think this will be correct. And then instead of saying point size large, I could say point size, say, small, and points, C points, comma, and I want line C points too. And the difference is that now, since I connected those from left to right, it should make one continuous line. Hopefully. Yeah, or at least it does after a little bit of debugging. Trouble is, it doesn't come out round here because it's just the going from 0 to 0.01 is a pretty big stretch. Actually, I think I did like the large point size, so I am going to switch that back to large. For now, I'm not sure why I'm wasting your time with this, except because it's fun to play with it a little bit once I get something done. Point size large, because this is just an artistic decision, and I'm not really an artist though, so I don't know what good artistic decisions look like, but you can kind of imagine that if we plotted every one of the points between there and there, we'd get something more nicely curved. What I want to do now, though, is I want to increase. Okay, I'm going to show this without folding it out and try to apply the sections that come down to the origin and all the squares that come out to the line. So, for instance, here we've got something saying for j equals I, negative I plus 1 to I minus 1. And I'm wondering what would happen if I just made it so j goes from negative I to I. And see what happens. Ooh, interesting. It looks like that generated the dots correctly, but it made it, oh, no, we need to go down. We need to go down here too. So maybe this would help if I said I equals 1. And that looks pretty good too. We need to increase something else by 1. So for instance here, let's make I less than or equal to, oh, wait, it was in the rendering, wasn't it? Well, anyway, let's actually go at least to Euclidean grid density plus maybe 2 here, so that we get more of that Euclidean space into the diagram. And now you can see it draws 2 rows above this section where that hits there. So here's something where I had Euclidean grid density minus 1 at the end of a table. Let's see if we can add 3 to that by changing this to plus 2. Let's see where that gets us. No. Oh, yeah, actually it did perfect on those. But let's just change that so that instead of being Euclidean grid density times 2, I'll just change it to top spot. And then that way, I'll come in wherever it says Euclidean grid density minus 1, I'll change that to top spot. And then where else can I change this? I can change it by moving it back here. And also changing this to top spot. And I still think there's more that I need to do by taking things over this way. And it might be something to do with this. I'm just going to make it 0 to n equals 0 to n less than or equal to Euclidean grid density and see if that fixes it. I'm not sure it will. And no, it didn't. But it did make another couple of lines there. That's interesting. How is that possible? All right, what it turns out is that top spot is going to be over here. So we're going to want to just go from 2, 0, 1, 2 in that loop, starting from there, all the way to top spot minus 2. So here it is, for n equals 2, n is less than or equal to top spot minus 1. Not top spot minus 2, top spot minus 1. And hopefully, yeah, that gives us a line to each spot. And there's one line missing down here, And I wonder if, well, notice that I've got 1, 2, 3 here, whereas everything else just has n squared and n plus 1 squared minus 1. It might be that I could start n equals 1 here, n equals 1, and here, or maybe even 0. Can I put 0 in here? And then, seems like I put 0 in here before and I ran into a problem. But let me see if n equals 1 will work, will do anything. Yeah. So what I'm going to try here is getting rid of the 1 and the 3, because the 1 and the 3 is taken care of by the command below. And then what? Check to see if it still produces those lines, which it seems to be doing. And then I gotta try to remember what SUMList did. SUMList started, well, I just have this intuition that 0 goes here. And with the miracle of computers, I can just check. No, I guess not. But it didn't make anything violently wrong. Oh, it removed the top things up here. That's interesting. Or no, it didn't draw any lines in here at all. So didn't draw any green lines through there at all. All right, I think the order I want it to go is 1, 3, 7, 13, 21, 31, 43. To go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, etc. And I want it to be the E grid of all those points. And I want it to be the line connecting all of the, or a line connecting all of those E grids to all those spots. And then I'll just put curly brackets around it to make it the beginning of a list. And I'll stick it into my program right here. EU spacelines equals, delete all that stuff, and just replace it with what I just typed down there. All right, moment of truth. Huh, it still didn't, it didn't include the point 0, 0. That's strange. Well, what about the Hubble flow stationary events? How do I add 0 to that list? Maybe I should go ahead and concentrate on that one. We'll just put a 0 in here. I think that's all it would take. Let's see what happens. Yeah, there we get a tippy tip down there. But look what else we got. We got all of the ironic time isoclines coming down. Ironic cosmological time isoclines screwed up. So now we're going to have to say, basically this is effectively added 1 to n hub observes. So no, really more, it's added 1 to events per Hubble observer. That's what it's added 1 to. So could that be handled here by, I think I've made this attempt before, subtracting 1 from events per Hubble observer? Yes, I think that may have been the most elegant possible solution. Now, as for the solution for the green, or for the Euclidean grid, getting all the way down to 0, I'm not sure how elegant this could be, because if I change this I to a 0, I don't know what kind of chaos I will unleash. But in order to get that first point to be the origin, I would have to change that I to a 0 to start off with. And changing that to a 0 does get this straight line here, but it causes a bunch of other problems. But I wonder how many of them could be taken care of just by adding +1 here and +1 here. Let's find out. That didn't quite fix it. Actually, no, it did. On the green lines, which is what I was editing there, it seems to have fixed it quite nicely. So what else do I need to do? I need to fix the red lines, which are the Euclidean timelines, which is this table here, starting from I squared to I squared plus 2I. But instead, well, I just wanted to go from I squared plus 1 to I squared plus 2I plus 1, maybe? Maybe so, yeah. That looked like a successful thing. Just going by guess and check right now, but it seems like it did the job. And now let's have a look at the swing down, or the fold out. I'll just change this to true and see what it looks like folded out, if it works. Yeah, and now everything goes all the way to the origin. So you can see all of those points along that line representing the speed of light have been mapped to the origin. How nice. I mean, actually not really that nice, but that's what the function did. So in the next video, I'm going to get to start really kind of doing some stuff with this, which will be cool. There are two main things that I want to try with it. One of them is, well, applying a scale factor to bring this stuff all in, particularly the scale factor t over, yeah, it'll just be t for this because this is 0.1 comma 0. So this is our t sub naught. So I want to apply a scale factor to each level. And then the other thing I want to do will actually be done in the Euclidean space. And then after the Lorentz transformation, we'll see what happens to the curves in this diagram. Another thing that I could do, wonder what I had these up to before, 30? I think for the kind of cool graph that I had before, I had those at 30. I could see if I can make that light cone a bit more dense. Where's that light cone? Right here. Let's multiply the number of points in that to 10 times as many. See what happens to that bottom part. And then I would also like to have the max rapidity be like 3. And let's see what that looks like. Um, doesn't look like much at all. Somewhere it ran into an error. Okay, I put everything back, but I changed max rapidity to 1.5, and it looks good there. Let's go to max rapidity 2. When I tried max rapidity 2, it comes to an infinite expression. How in the world does that happen? Okay, here's what it looks like with max rapidity 3 in the original form. So when I put max rapidity 2, maybe, or max rapidity 3, something's going on with something. With the max rapidity at 1.5, things don't look quite so ridiculous. So maybe it's having trouble with some of the points up here and up here. Okay, so it definitely has some problems with the fold-out function for if I apply too high of a maximum rapidity to the Hubble observers. I'm not sure how to resolve that, but I imagine we'll figure that out eventually. Thanks for watching.